Great. So last but not least, we have Brice Huang, who is currently a postdoc at Stanford and will be joining Yale as assistant professor in statistics and data science. He's done a lot of incredible work in high-dimensional probability and intersections with statistical physics. And today he'll be capping things off by telling us about how diffusion models and MCMC can sample from spin glasses.
Okay. Yeah. Thanks for the introduction, and thanks everyone for coming. So this talk will be about a sampling from spin glasses, which are a very concrete model of target distribution. But along the way, we'll see some general tools for analyzing diffusions. And diffusions will show up both as an algorithm and as a proof method. So first, this talk is based on two papers with these wonderful collaborators. The first paper is with Andrea Montanari and Huituan Pham, and the second is with Siddharth Mohanty, Amit Rajaraman, and David Wu. So I'll begin by giving some background and motivation for the problem that we'll study. The guiding question of this talk will be to sample from a high-dimensional probability measure. And we'll consider measures parameterized in this form, where you're given access to this log density V. And your goal is, using any polynomial time algorithm, output a sample from this distribution. And this is a useful subroutine that shows up in many downstream tasks, including inference, integration, optimization, and many more. Some settings of this problem are well understood. So if your target measure is, say, strongly log concave, then we know how to sample from this, and we know, I guess, very optimal algorithms for sampling from this. Many people in this room have worked on this. In this talk, we'll focus on a setting where the target measure is very not log concave and instead highly multimodal. So let me introduce the target measure that we'll study. This is called the mean field spin glass. You can think of it as a probability measure where the log density is a random polynomial with Gaussian coefficients. And we've seen some of this earlier this week in Holden's talk. So for example, you can consider this random cubic in n variables, where you write down all n cubed monomials of degree 3 and put an independent Gaussian in front of each one and add it up. Then you can construct this Gibbs measure. It's the measure supported on the n-dimensional sphere, whose density relative to uniform is e to the beta h. So here beta is a real parameter called the inverse temperature, and this sort of lets you dial how hard the problem is. So if beta is 0, then this is the uniform measure, and this is, of course, easy. But if beta is large, then this is a very not log concave measure, and it's expected that sampling from this is hard. In fact, if the weights or if the coefficients were worst case, then this is known to be NP hard. So that's one example of this mean field spin glass. More generally, you can consider a linear combination of different degrees. So not just degree 3, but you can mix different degrees together. That's called the mixed p-spin model. And something else you can do, which we won't do in this talk, is consider models on the cube instead of the sphere, like the SK model in Holden's talk. And these spin glass models have a wide variety of downstream applications. So they're a canonical prototypical model of a disordered probability measure. And they show up in places like if you take a random constraint satisfaction problem like max cut on a big random graph and suitably recenter and rescale, then you get exactly the ground state of a spin glass. And there's also connections to things like the loss landscapes of neural networks and posteriors in high-dimensional Bayesian inference. So next, I'll introduce the algorithms that we'll study and state our main results for these algorithms. So to restate the problem, we're given a random instance of this spin glass Hamiltonian, and we want to sample from the Gibbs measure. So more precisely, our goal is to devise a randomized polynomial time algorithm that's given some representation of h as its input, and its goal is to produce an output whose distribution is close to this target measure mu beta. And because h is random, the type of guarantee you'll want is this holds with high probability over h. And we want to know at what inverse temperatures beta you can do this. So perhaps the most canonical algorithm you can study is the Langevin dynamics. So this we've seen many times this week. It's described by this SDE, and this is known to have stationary distribution equal to the Gibbs measure. Okay, there's a slight lie here. What I wrote is the SDE for the full space Langevin dynamics, but you can write an analogous version for the sphere. And this gives you a polynomial time sampling algorithm if the dynamics mix rapidly, meaning that in a polynomial amount of time, you get an iterate that's close in total variation distance to the actual target. And if this happens, then you can get an actual algorithm out of this by discretizing the dynamics, do some sort of Euler discretization, and then you can implement it. Now, there's a class of problems where you want to get the best possible polynomial runtime. And for that, you want to kind of figure out the smartest way to discretize this. This is a hard and interesting problem that many people in this room have worked on. In this talk, we'll just be interested in getting any polynomial runtime at all. So we're happy to be very naive. Like if you discretize time by n to the minus 100, then you get an n to the 100 time algorithm. So we won't really worry about these discretization issues. But let me now be a little more precise about the type of guarantee we can hope for. The ideal kind of guarantee is rapid mixing from a worst case initialization. So if this happens, then you can just start anywhere, run your Markov chain, and you'll get a sample. But unfortunately, this isn't always possible. So let's compare these two scenarios. In the scenario on the left, you have a well-connected measure. And on the right, you have a measure where most of the mass lives in one blob, but you have these little islands that are poorly connected to the bulk called metastable states. Then in the first scenario, you can hope to mix from even a worst case initialization. But in the second one, this simply can't be true because if you initialize in one of the islands, then you'll get stuck. But you might still hope that in the second world, if you initialize at random, then you'll succeed. So the hope is that you'll mix to the measure condition on the big cluster. And maybe you miss the little clusters, but you don't really mind because they account for a vanishing fraction of mass anyway. And just to complete the picture, you might also have a world where the measure is shattered, consisting only of these little islands. And here, any kind of dynamics will fail to mix from any initialization. So we're now ready to state a first version of our results. So it's conjectured in the physics literature that as you vary the inverse temperature beta, your Gibbs measure goes through these different phases with these very precise phase transitions. So up to a uniqueness threshold, you have this well-connected picture. Then up to a shattering threshold, you have mostly connected with some metastable states, and then you're shattered. And as we said, we expect that this corresponds to these qualitative behaviors of the Langevin dynamics. In the shattered phase, there's a stronger prediction that not only does the Langevin dynamics fail to mix, but actually sampling here is computationally hard for any efficient algorithm. So to summarize, the main physics conjecture about sampling from this model is that you can sample up to shattering and no further. So up to shattering, even a very simple algorithm, Langevin dynamics from random initialization, is expected to work, and beyond shattering, nothing works. However, both sides of this picture are still open. On the algorithmic side, the issue is that even though we expect the Langevin dynamics will work, the analysis of this algorithm is hard to do in a sharp way. So our main result will be that two algorithms that are not the Langevin dynamics work up to a inverse temperature that we'll call beta stochastic localization, which I'll say more about in a second. These two algorithms are called simulated annealing and algorithmic stochastic localization. This beta SL does not equal shattering, but it does get pretty close. So for the pure p-spin models, it is smaller than beta shattering by a constant factor of about 0.8. So next, I'll describe what these algorithms are, but are there any questions up to here? Cool. Oh, yes.
E is quite natural. Do you think in general it always look like this?
Say that again.
So where does the square root E come from? Is there any intuition?
Like, okay, both beta SL and beta shattering turn out to have some like parametric form in terms of p, and then in the large p limit, it just
I see.
yeah.
Do you think that this constant will show up in other settings beyond singulars?
I don't think so. I don't think it's a particularly deep constant.
Okay. That's
Yeah. So the first algorithm that we'll look at is simulated annealing. And you can think of this as just Langevin dynamics where you gradually ramp up the value of beta. So this algorithm will work in a large number of discrete phases. In each phase, we set a artificial inverse temperature, beta L. So this will interpolate from 0 at the beginning of time to beta at the end of time. And in this phase, we'll just run Langevin dynamics with that effective inverse temperature, initialized from the output of the previous phase. So in a picture, this is what the algorithm is doing. Like at an early time, you'll sample from a density that's kind of artificially flatter than it's supposed to be. And as time goes on, the density that you'll sample from becomes closer to the real one. And any peaks in your density will become more pronounced over time. So this is a natural and long-studied algorithm for both sampling and optimization going back to physics works in the 80s. But until now, rigorous guarantees for this algorithm have been somewhat scarce. So that's simulated annealing. And now for a completely different algorithm. So this is stochastic localization, and I guess we've seen it many times already this week. So maybe this slide will be reviewed. This is an algorithm to sample from this target measure mu. And we'll think of this in a Bayesian inference type of setup. So let's imagine that nature samples some secret x star from the target measure, but doesn't reveal it to you. Instead, it shows you this Brownian motion with unknown drift x star. So in this picture, imagine if x star is uniform from the vertices of the hexagon. You don't see where x star is, but you get to see this blue trajectory. Then you'll form a path of posteriors, which is just your Bayesian posterior on x star given the Brownian path that you've observed so far. So roughly at early times, you don't really, the position of the Brownian path doesn't really tell you anything about x star, but as time goes on, you can read off x star for the long-term direction of the path. So this sequence of measures is the stochastic localization process. It turns out that the value of the path of the last time is a sufficient statistic for the whole path, so you can also just think of it as the posterior of x star given yt. So this is the SL process, and as time goes to infinity, this will of course localize to a delta mass at the secret x star. So that's stochastic localization, and you can use it in two different ways. The first way is you can use it as a sampling algorithm. So if you can algorithmically simulate this stochastic localization process, then you can just run this to the end of time and then read off a sample from the end. And the main challenge in doing so is you have to do this, you have to algorithmically simulate this without having access to X star to begin with. This idea was introduced in papers by Ahmed, who is here, Montanari, and Selke to sample from the SK model. And as we saw earlier today, this is also equivalent with some time reparameterization to denoising diffusions. The second way you can use stochastic localization is as a proof technique. So it turns out that suitable control of the SL process implies functional inequalities for the target measure mu, which then imply rapid mixing for Markov chains like the Langevin dynamics. So these ideas originated in convex geometry and led to important breakthroughs on the KLS conjecture. So our proof that simulated annealing succeeds will also go through this type of pathway. So we're now ready to state our main results for sampling from the spin glass. So I'll plot the inverse temperature parameter beta on the vertical axis. And I'll first state what was previously known and where our results fit in. It's expected that for any beta bigger than the shattering threshold, the Gibbs measure shatters and all polynomial time algorithms will fail to sample. Rigorously, it's known that suitably stable algorithms will fail to sample in this region. And it's also predicted that anywhere up to shattering, the Langevin dynamics from random initialization will succeed. In the way of rigorous results, it's known that at small enough beta, so high enough temperature, Langevin dynamics will mix rapidly from even a worst case initialization. It's also known due to a recent paper by Belarus and Jagannath that above a threshold beta uniqueness, there indeed exist metastable states. So anywhere above this beta uniqueness, Langevin dynamics will provably mix slowly from a worst case initialization. And this beta uniqueness is a natural barrier for the many analyses of Langevin dynamics, because often when these analyses work, they also show rapid mixing from worst case. Algorithmic stochastic localization will get past this, this barrier, and works by Ahmed, Andrea, and Mark produced samplers that sampled with vanishing Wasserstein error. Our main result will be a sampler that goes through the algorithmic stochastic localization framework and succeeds with vanishing total variation error. This works up to a explicit inverse temperature beta SL. And we also get a matching hardness result that anywhere above this beta SL, a class of stochastic localization-based methods will not succeed. And our second result is that in the same range of temperatures, simulated annealing will also succeed. So we expect that simulated annealing will work all the way up to shattering, and the fact that the result stops here is an artifact of the proof. Questions about this?
What is the nature of the hardness result? You said that result is still like only hardness against stable algorithm?
It's even weaker. It's hardness against a class of implementations of algorithmic stochastic localization. Yeah. So I guess I'll have one slide about this at the end. Yes.
And is the TV error for the simulated annealing stronger than the?
Yes. So here, for the first result, the TV error is something like n to the small constant. I think if you push it, you can get like 1 over root n or something. here the TV error is like stretched exponential, so e to the minus n to the fifth or something. Okay, so in the rest of the talk, I want to outline some of the ideas that go into the analysis of these algorithms. So I'll begin with algorithmic stochastic localization. So let's recall the setup of stochastic localization. Nature generates a secret from the target measure, and we observe this Brownian motion with unknown drift. Then the key algorithmic idea from the paper of Ahmed, Andrea, and Mark is that even though we don't know x star, if we think of x star as itself random, then we can still generate for ourselves this sample from this SL process and thereby produce a sample. So this is possible thanks to the following equivalent description of the SL process. From our point of view, where we get to observe the Y process, but not the secret X star, we can think of this Y process as a SDE, where the instantaneous drift is the posterior mean. So I think Kevin's talk today already described this. And this gives you a autonomous SDE. So the coefficient at time t depends only on information available before time t. So this lets you simulate this SDE even if there was no ground truth x star to begin with. And this reduces sampling to posterior mean estimation. So if you're able to estimate the mean along this trajectory of measures, then you can simulate the Y process for yourself and thereby produce a sample from the target measure. And the posterior measures turn out to have a relatively simple form. So this will be a short calculation. This is the posterior of x star drawn from the Gibbs measure, given some observation of this stochastic localization process. So we can write this by Bayes' rule just as the prior times this likelihood of seeing this realization of the Y process. And skipping some calculations, you'll find that the posterior is simply the prior exponentially tilted by Y. So this means that the measures you encounter along stochastic localization are just the original Gibbs measure with this randomly evolving exponential tilt. And the game is now to estimate the mean of this object. So the paper of Ahmed, Mark, and Andrea do this by using approximate message passing to estimate this mean. And so AMP is a, by now, very well-studied algorithm in high-dimensional statistics. And this will result in an estimator with this type of accuracy, that the mean square error is little o n. Think of this as saying that the estimator is correct to leading order, since points in our state space have typical square norm of order n, so little o n sort of means correct to leading order. And this will lead to a sampler with this correct to leading order type of Wasserstein guarantee, that you can couple a algorithmic sample to a true sample with this little o n squared error. It also implies sort of asymptotically accurate samples in the sense of sublinear KL divergence. The main thing we do to upgrade this to total variation is to develop a improved mean estimator with mean square error little o1 rather than little o n. So this will sort of start with the AMP estimator and then find a suitable correction term that allows us to upgrade this accuracy. And it turns out that this gives the required TV guarantee. I'll say a little more about how this is done at the end if there's time. Next, I'll switch gears to talk about our analysis of simulated annealing. So I'll begin with a general pathway for proving rapid mixing of Markov chains through functional equalities such as Poincare inequalities. So for any target measure mu and test function f, you can define this Dirichlet form, which is the expected square gradient of the test function. And you can think of it as a local notion of variance of this test function. And we say that the target measure mu satisfies a Poincare inequality with some constant c if this variance is bounded by the Dirichlet form for all test functions. And this Poincare inequality turns out to imply rapid mixing even from a worst case initialization. So it turns out to imply that the chi-square divergence of your sample to the target will contract exponentially. So the way to read this is nu is the measure that you initialize from, and pt nu is the measure you get from that initialization running Langevin dynamics for time t. So this says that your chi-square divergence will decay exponentially. So then if this holds with a constant c that's not too small, then this implies that even from a worst case initialization, you'll mix rapidly. However, as I alluded to earlier, this is often too much to hope for, because in the applications that we're interested in, if there's metastable states, then we already know that mixing from worst case cannot be true. So we'll need a more granular tool for the applications we care about. So one of our main ideas is to look at what's called weak Poincare inequalities. So this is a variant of a Poincare inequality that turns out to be more tolerant to metastable states. So it includes this extra parameter delta. And the statement is like a Poincare inequality, except there's this extra error term that depends on delta and on the infinity norm of f squared. So this is the term that will sort of account for the metastable states. As for how big things are, think of c as like a big constant and delta as something that's extremely small, like maybe a stretched exponential type of size. Then just like how a Poincare inequality implies rapid or exponential contraction of chi-squared, a weak Poincare inequality will imply this sort of almost exponential contraction. So you'll exponentially contract, but you'll bottom out at some value that isn't zero. And this thing you bottom out at will depend on delta and on the likelihood ratio between your initialization and the target. So the upshot of this is that if you initialize at a warm enough start, which we'll take to be a measure whose L infinity norm likelihood ratio with the target is not too big, then you mix rapidly up to a small error. And this notion of rapid mixing from warm starts turns out to play really nicely with simulated annealing. So this is how we'll end up showing that simulated annealing succeeds. And roughly the reason is that in simulated annealing, you have a whole bunch of stages, and the measure that you're trying to sample from in each stage is a warm start for the next one. So you get to kind of chain these things together. So recall in simulated annealing, you have these stages. In each stage, you define this effective inverse temperature and run Langevin dynamics on this target measure with the intermediate temperature. Then the point is that each measure in this sequence is a warm start for the next one. So a weak Poincare inequality lets you sort of inductively argue that up to stage L, you've roughly mixed to mu L. So in the first stage, you mix to mu1. And then because mu1 is a warm start for mu2, in the second stage, you mix to mu2, and so on and so forth. So this will be the overall proof strategy. So this builds on a staging warm starts idea that was introduced in an earlier paper by Ahmed, Aldan, Gassari and Piano, and this was an inspiration for us. Okay, so this reduces the problem to proving a weak Poincare inequality. And the way that we'll do this will also be parallel to a technology for proving Poincare inequalities that's been highly influential in the literature. So we've already seen this notion of exponential tilt of a probability measure. There was a very influential framework called localization schemes and related to spectral independence, introduced by Chen and Eldon, whose overall message is that if every exponential tilt of your target measure has bounded covariance, then your measure satisfies a Poincare inequality. So this gives you a pathway for proving Poincare inequalities, and through that, rapid mixing. We introduce a parallel version of this tailored to proving weak Poincare inequalities, which roughly says that if your target measure has bounded covariance under a family of random tilts with high probability, then it satisfies a weak Poincare inequality. And just to be more precise, the family of random tilts that will show up are precisely the tilts that you get under stochastic localization. So formally, if along a trajectory of stochastic localization with probability 1 minus delta, all the measures you see have bounded covariance, then you have a weak Poincare inequality with error parameter delta. So then sort of the overall input to this pipeline is to show this high probability covariance bound. So okay, just to take stock of where we are, we've now seen these two parallel pipelines for proving guarantees on rapid mixing from worst case initialization and simulated annealing. And the way you would use these is you prove these two inputs in whatever application you care about using whatever means necessary, and then these pipelines will give you the conclusion you want. I'll dive a little deeper into this step, because this is really where the meat of the argument is, and this is also where the stochastic localization process will enter. Let me first explain why a worst case tilts covariance bound implies a Poincare inequality. So this is maybe the main idea of the Chen and Eldon work. So let's say we want to show a Poincare inequality for this target measure. Then we'll run stochastic localization for a big constant time t. And what stochastic localization lets you do is sort of go around a rectangle. So you run localization to time t, and you get a random measure mu t. So this expectation means expectation over that randomness. It turns out that these two inequalities that I wrote hold for sort of simple reasons, roughly. This one because the Dirichlet form is a supermartingale, and this one because localized measures tend to have a Poincare inequality for somewhat simple reasons. So the main difficulty is to compare the variances before and after localization. So if you can say that localization didn't decrease the variance too much, then you get to go around the rectangle and get a Poincare inequality. And this is where the main idea of Chen and Eldon enters. So they think of this variance as a stochastic process indexed by time t, and they stochastically differentiate to get this stochastic differential inequality. And the drift turns out to be governed exactly by the covariance of your measure. So under the worst case tilts covariance bound, this covariance term is bounded by a constant almost surely. So this turns out to imply that your variance can't decrease too much over localization. So that's for the worst case tilts covariance bound. We'll use a similar strategy to prove that random tilts covariance bound implies a weak Poincare inequality. So we'll sort of run the same argument, but now with a stopping time. So we define the stopping time tau to be the first time that the covariance exceeds some big constant k, but we cut it off at a big time t if it doesn't happen. Then, as before, we have this stochastic differential inequality representation of the variance. And if you just look at the variance at time tau, then nothing bad can happen before time tau. So the variance at time tau is controlled by the variance at time 0. So now we just need to relate the variance at time tau to the variance at time t. So this is where the high probability covariance bound enters. This bound exactly says that the probability that tau is not t is small. So then we can break up this time tau variance into the good term, which is time t, and the bad term, which is the contribution of the event that tau is not t. And we can bound this last term extremely crudely by just the probability of this event times, and you L infinity bound the variance. So if you put this together, then you get to relate the time 0 variance to the time t variance and a small error. So if you go around the rectangle again, then this will prove a weak Poincare inequality. So I'm almost out of time, so I'll wrap up. So in this talk, we've seen these two sampling algorithms, stochastic localization and simulated annealing. And both reduce to showing something about the stochastic localization process. So to analyze algorithmic stochastic localization, the thing we want to say is that we want to produce a mean estimator of this localized measure with this type of accuracy. And to show that simulated annealing succeeds, we need to prove a high probability bound on the covariance of these localized measures. And most of the technical content in these papers is to show these inputs. Since I'm almost out of time, I'll skip this part and feel free to ask me offline. So let me skip this slide. I'll just mention one more result, which is on the opposite side of hardness. So we can consider a sort of generalized version of stochastic localization, and we'll end up showing that, so this will only make the algorithm stronger, and we show that even this will fail above beta stochastic localization. So in ordinary stochastic localization, nature samples x star from the target and then shows you a Gaussian channel observation of x star. In this generalized version, you'll also get to see Gaussian channel observations of various tensor powers of x star. So formally, you get to see a whole sequence of Brownian observations. In the pth element of the sequence, you get to see the pth tensor power of x star noised by this Brownian tensor with n to the p entries. And here lambda pt is the information schedule of the pth channel. So these can be sort of arbitrary increasing functions on the real line. And our main result is, or our hardness result here is that if beta is bigger than beta SL, then even this generalized version of algorithmic stochastic localization will fail. And the mechanism of the failure is that there will be times when AMP will not be able to estimate the mean. Why is this? Well, it turns out that when your beta is this big, then there will be times when the mean of your measure will move violently in ways that AMP just cannot follow. So here's a cartoon. Imagine if you have a measure that's concentrates roughly on two parallel bands, which are an extensive distance apart and parallel to each other. And like the field is pointing in this direction. Then if you change your field by a little bit, you can make the measure concentrate on just this band or just this band. So by perturbing the field a little, you can get the mean to move a lot. So this type of scenario will turn out to happen, and AMP will not be able to follow the mean here. And the same mechanism will also break our proof of the weak point grade inequality, because at a time t, when the measure is like straddling these two bands with, say, at least 0.1 mass on each, the covariance simply will not be bounded.
And what is the algorithm that's associated with this process? Is it on the space of all of these tensor powers?
Yeah. So I guess in vanilla stochastic localization, you just get y1, and you can autonomously simulate this y1 by some SDE. So here you have some coupled system of SDEs that involve all the y's, and you autonomously simulate that.
I see, because there's this work in the setting of tensor PCA that showed that if you over-parameterize, then the landscape changes. So here you're kind of saying no trick of that sort would work with this.
Yeah, that's right. Yeah, we were a bit surprised by this. We thought this would help.
No, I mean, okay. We can talk offline.
Okay.
This is clear.
Yeah. Okay. Yes.
Just make like when you say fail to estimate mean mu t, you mean like there's some range of t, intermediate range of t's for which?
Yeah. There's some range of t's where I guess AMP will converge to the wrong fixed point is what happens.
But when the noise is small, so you're just estimating marginals of the base measure, is this believed to be true?
Are
I guess there's a
what?
sign thing, but
Are you saying like when the sign information is small, like if t is 0, say?
when it's when the side information is small. Yeah.
Sure. If t is 0, then I think the relevant AMP fixed point is 0, and this works as a mean estimator. So I think for t small, this is fine. But yeah, there's some like I think tensor PCA is maybe the right intuition here. Like there's some range of t's where like after you specialize to some band, like it looks like you're solving a tensor PCA problem above the information theoretic threshold. Okay, so yeah, to conclude, we studied these two algorithms for sampling from a spin glass Gibbs measure. For algorithmic stochastic localization, the main thing to do is to get an improved mean estimator. And for simulated annealing, we show this pipeline where high probability covariance bounds imply weak point grade inequalities, which imply sampling guarantees. So I'll conclude with one open question, which is to fill in this remaining gap between beta SL and beta shattering, and to provide an algorithm, really any algorithm, doesn't have to be one of these two, that works up to the full shattering regime. And because of this hardness result, this will probably involve different ideas than what was presented here. So yeah, thank you.
Imagine that you expect simulated annealing works all the way to shattering. So is that for average case or for like the worst case?
So probably simulated annealing from even a worst case initialization should work up to here, because if you do Langevin from a worst case initialization, you can get stuck in an island. But simulated annealing, like in the early time steps, you can hopefully escape the island, and then it should work. But proving this is a different matter.
How large do you expect the expectation of the operator norm of the covariance in this region?
Expectation, like at a fixed time, or
Say at a fixed time, yeah.
or is it like expectation of supremum over time
No,
of?
no,
Oh,
just
oh,
no
oh,
supreme,
oh,
just
oh, okay.
expectation.
Oh gosh. Yeah, okay. I don't know off the top of my head. Like there does exist a time where the operator norm will be like root n scale, because like at the time when your measure is like straddling the two bands, then it is actually of root n scale. But I don't know how long like that window of time. Like I think it'll happen in like a random window of time.
Okay.
But I don't know how like long that random window of time is. Like maybe it's like 1 over root n. Or, I don't know.
Okay, so
Yeah.
so there's a possibility that like for I guess it's you either look at a trajectory and what happens on that trajectory, or you can look at a time and then expectation along the time. So it's possible that the expectation for fixed time is actually constant or no.
Yeah, that seems possible.
Okay.
Yeah.
Are there natural examples of distributions which satisfy weak Poincare but aren't TD close to a Poincare distribution?
I don't think so. In fact, I think after we wrote this, I think Siddharth came up with a proof that if you have he wrote this for discrete space, that if you have a weak Poincare inequality, then if you like do some surgery on the measure, you can get a TV close measure that has an actual Poincare inequality. So probably these are the same.
So that's kind of interesting because here you have a gap between the region where you have worst case mixing and the region where you can mixing from simulated annealing. So I thought this already provide an example where you don't have like you're in the region where you're supposed to be slow mixing from worst case, you shouldn't have a strong Poincare inequality. But are you saying that in this region you shouldn't also expect to have a weak Poincare inequality?
No. It's just a different measure. Like the one that satisfies the Poincare is just a different one. It's not the one you started.
That's true.
Yeah.
But I guess when you say the surgery, I'm kind of curious what's the nature of.
I get the surgery is just the big island, just the big.
Yeah, just
You just keep other
just kind of
then
just squish the small islands and
then
then
that's not
yeah.
interesting.
Yeah. Yes.
So the bound on the covariance, I guess, like it's crucial that you're in the 3-spin or the p-spin. It wouldn't work on SK, the bound on the covariance that you used within the argument of the Poincare inequality.
I see. For the sphere, I think 2-spin is also okay.
For the
Yeah. So.
for the spherical SK, what do you mean for the spherical?
Yeah. You're talking about how we prove this thing, right?
Correct.
Yeah, so this is by a moment method plus some concentration tricks. So I think maybe what you're referring to is like, if you had a 3-spin model, then you can prove this type of thing with like literally just like second moment method.
Right.
So I guess in our actual proof, what we do is we handle the degree 2 and degree 3 and above parts separately. So degree 3 and above, we handle the way you expect.
Yeah.
For degree 2, there's a connection between the spherical SK and some random matrix. Okay, so
But
like
can you execute this argument without the high degree part if I just give you a quadratic?
yes, yeah.
So this result also applies to this SK model.
On the sphere, not on the cube.
Oh, you're on the sphere.
Yeah,
I forgot.
yeah.
Okay.
Yeah, on the cube, I don't know how to do this. Like on the sphere, we're abusing some connection between the spherical SK and some random matrix estimates.
So just trying to understand, I thought on sphere, on SK, on like non-spherical SK, you don't have a gap between fast mixing of Glauber and like fast mixing of simulated annealing. But it seems for spherical, do you have this gap? For P equal 2. I'm just trying to understand for P equal 2, spherical SK, do you have a gap between region where Glauber mix fast and region where simulated annealing mix fast?
For p equals 2, I think all of these numbers end up being the same.
Okay, so they're
Yeah,
all the
all of these numbers are 1. So, yeah. When it's only when when you have mixed p spins or p is bigger than 2 where
So beta SL is also
equal to 1, equal to beta RS, equal to beta unique.
See you guys in 2027.
Thanks for organizing.